Welcome everyone to this session. In the previous session, we looked at the block diagram of a charge pump PLL, and we also drew the small signal model of the charge pump PLL. So, today in this session, we will look at the analysis of the charge pump PLL. So, our PLL included a phase frequency detector followed by a charge pump. The charge pump was realized using switches and current sources. So, we had two current sources, up and down. So, this was connected to VDD, this is ground. As you see, these are up and down signals which actually open or close the switch. The output of the charge pump here is the current ICP in caps, and you have a loop filter RNC or RNC1. This loop filter output is connected to the oscillator in this manner. Okay. So, here this is your reference signal. I will write this as reference, and this is your output signal. The current which comes out of the charge pump, I will write that as a small ICP. See, capital ICP is the current in the charge pump, and depending on which switch is open, what current is flowing, that I am specifying with ICP. This node voltage is control voltage. Okay. Now, in this actual circuit, if we look at the reference and the output pulses at any given instant of time, you may have phase error some phase error at any given time, reference and output. So, deliberately I am showing you what happens when you have some small phase error at that particular instant of time. We can have for the other one, let me just draw the negative phase error, for example, like this. So, in response to this reference and out pulse, you will have up and down pulses going like this. This will be your up pulse, and corresponding down pulse, it will actually remain 0 ideally, and the down pulse goes high when you get a rising edge on the out pulse before the up pulse. Okay. So, here I am just giving you one example where your out pulse goes high before. So, your out pulse goes high, and then when you have a rising edge on reference, your out pulse goes down. So, effectively your reference is triggering this, your output is triggering this. Similarly, here. So, these are your reference and out pulses. In response to these reference and out pulses, we have ICP, and a small ICP, this current should be equal to our ICP current. So, when your up pulse goes high, you actually close the switch and ICP flows here. So, you have ICP current flowing in the given direction. The current value is capital ICP. Okay, it flows for this much amount of time, and then when down pulse goes high, right, your up pulse goes low. So, the switch is open again, down pulse goes high, this switch gets closed, the current ICP flows in this direction. So, giving the direction, notifying the direction by the sign, your ICP current is like this. This value is you can say minus ICP. This is how the current flows. Now, in response to this current, you are going to have a change in the voltage, a control voltage change, okay. And this control voltage V control happens to be, you will take a jump ICP R, it will integrate and it will come back by ICP and then it remain constant. Okay. When you get a negative pulse, right, then what you will do is you will take a minus jump of ICP, it will integrate in the opposite direction and your control voltage will become like this. Okay. So, this is what is happening to your control voltage. Now, based on the control voltage, your frequency will change and the phase will change and the PLL is going to lock. Now, for this particular charge pump PLL, we drew the small signal diagram and a small signal diagram was shown like this. You have the phase error. So, phi reference, okay. Detect the phase error. So, effectively you are subtracting the output phase by output phase from the reference phase. You get the phase error. The phase error output, you have a PFT. So, PFT plus charge pump combined gain is equal to ICP by 2 pi. If you want to write it separately, we can write it as 1 over 2 pi for phase error detector gain in a steady state and this is ICP. Okay. So, here you can still say this is V phase error detector VPD, or in our case PFT, and this is the charge pump current, right. So, this current goes through the loop filter as shown here, R and 1 over S C1 is the capacitance impedance, and then it has a VCO whose response from control voltage to output phase is KVCO over S. Okay. So, this is the small signal model of the charge pump. Okay. This is phi out. So, in the previous session we approximated the gain, the average or the combined gain of the PFT plus charge pump as combined gain of PFT plus charge pump was equal to ICP by 2 pi. Okay. So, this is that was an approximation actually. If I look at the actual operation and our modeling, there is some difference and we will tell that okay, this difference is actually negligible in many cases. First, you can say approximation here is what we are considering is with respect to the phase error. So, this is our, this corresponds to the phase error, delta t error or phase error, whatever you call it. Okay. So, the phase error gets multiplied by ICP over 2 pi and that current is there. So, the average current, ICP average current, if we would like to write based on the phase error which we have, this is an approximation which we are using by the way. So, this current is like this. This is an approximation. What is the value of this current? The value of this current is ICP by 2 pi times the phase error. Okay. which effectively is you can say ICP by 2 pi. Phase error is nothing but 2 pi times delta t by t, right. So, these things cancel out. If you look at it, the average, the total charge which I am going to add here is that is the area under this curve. This area under this curve is equal to ICP times delta t, which corresponds to the phase error. Here also this is this value ICP times delta t by t. If you integrate it over time period t, which is the reference clock period, you will get the same value. Okay. So, our modeling is slightly different from our actual operation, and under the assumptions that okay, our frequency of operation or the frequency at which the changes are happening in the system, that frequency is much lesser than the frequency at which we are clocking the system. Okay. So, well, under those assumptions you can approximate your charge pump current like this. We will see later that when our bandwidth of this whole loop is much higher, right, is much higher, or it becomes closer to reference frequency, then our assumptions will not be valid. So, for now assume that the assumptions which we have made, those assumptions are valid, and the relationship between the actual operation and the operation in our small signal model is as shown. Let me just remove V control from here, because now with respect to this ICP, V control will change. So, with respect to this small signal model, the thing which we need to understand is that whether this model is stable or not, and what are the gains from different nodes to the output. Okay. So, for the small signal analysis of charge pump PLL, small signal analysis of charge pump PLL, okay, our loop gain, which is defined as the gain around the loop, that is this loop we are talking about. The loop gain of the system is ICP by 2 pi into R plus 1 over SC times KVCO over S. I have been using C1 in all these cases. Okay. So, this is nothing but you can write it simply ICP by 2 pi S square C1 into 1 plus SR C1 and KVCO comes here. Okay. So, this is our loop gain. There are two poles. So, omega P1 and omega P2, the two poles are at 0, and the 0 for this transfer function is at 1 over R C1. Okay. The angle of the loop gain is given by, you see two poles, they contribute minus 180 degree plus tan inverse of, because of 0 you have an additional phase omega by omega z, or you can say minus 180 degree plus tan inverse of omega R C. Okay. Now, just to plot this particular loop gain, the help of Bode plot, we have magnitude of loop gain versus omega. This I will plot in dB 20. So, you have minus 40 dB per decade starting from 0 frequency, and then you will have a 0, and based on the 0 you will have this is going to be minus 20 dB per decade. Okay. This frequency is the 0 frequency, the frequency at which you cross the unity gain or 0 dB line, right, that frequency is unity gain frequency. Corresponding to this magnitude plot for the loop gain, you have the phase plot, angle of loop gain. The starting phase happens to be minus 180 degree. So, I will just plot this. So, there are two frequencies which are important right now. One is the 0 frequency. So, you start from minus 180 degree, which is this I make at as 90 degree. When you come to the 0 frequency, you are going to add a phase of 45 degree. So, it will become minus 135, and then from minus 135 it is going to, at infinity, this frequency is going to be minus 90 degree. It will not cross minus 90 degree. Okay. So, to check the stability of this particular loop, right, what we need to see is what is the phase margin, the difference between minus 180 degree and your actual phase at unity gain frequency. So, the phase margin is given by minus 180 degree minus of angle of loop gain at unity gain frequency. Okay. This you substitute it back, you will find this is equal to tan inverse of omega by omega u by omega z, or written same as tan inverse of omega u times r c 1. Okay. Now, how do we know what is omega u? Well, you can, to find omega u, you can very well find omega u such that the magnitude of loop gain is equal to 1. Right, you substitute it back, you will find what is omega u, or the other way is an approximate way. So, you can do an approximation, quite often it works. An approximation is magnitude of loop gain is equal to 1 implies. So, here what you see is this is the gain which we are looking at. So, this I will write as ICP times KVCO divided by omega u square 2 pi omega u square C1 times omega u r C1 is equal to 1. This is an approximation. Okay. So, what I am saying here is that 1 plus SRC is actually equal to SRC, and the reason you can say at omega u, the reason you can say that omega u is much larger than omega z. So, 1 plus j omega u by omega z is approximately equal to omega u by omega z. This is the approximation. If I do this approximation, it goes off, C1 goes off, and then omega u is actually equal to ICP KVCO times R divided by 2 pi. So, we have seen the loop gain of the PLL. In order to calculate the phase margin of the PLL, this is equal to the separation between your actual phase and minus 180 degree. So, let me just redraw this, where you start from minus 180 degree and after some time this goes to minus 90 degree. Okay. So, given the omega u frequency, this is the value which we need, which is going to be minus 180 degree plus tan inverse of omega u r c minus of minus 180 degree, which is tan inverse of omega u r c. Okay. Now, the question is how to find omega u. Well, unity gain, for unity gain frequency omega u, you have modulus of loop gain at omega u equal to 1. Okay. So, you find the omega u from that loop gain expression, or you can also write it as ICP times KVCO into 1 plus SRC divided by S square 2 pi S square C1. this magnitude equal to 1 at s equal to j omega u. Okay. Now, here I can do one substitution, approximating first that omega u by omega z is much greater than 1. It implies that ICP KVCO times omega u RC divided by 2 pi omega u square C1 is equal to 1. Given this approximation, omega u is equal to ICP KVCO times, you have the C1 cancels out, omega u goes away, ICP KVCO times R divided by 2 pi. So, you can substitute this back here in the phase margin stuff, and this is going to be your ICP KVCO by 2 pi, right, into R divided into R C1. So, this will give you the phase margin for the PLL. Okay. And looking at the plot, we know that the phase margin is greater than or very close to 90 degree. Okay. So, this system is going to be quite stable. Okay. If you have a 0, that is why we earlier also introduced a 0 to make the PLL stable. Okay. Thank you.